So thank you very much for everyone that's coming for the second lecture. Let me just start giving a brief reminder of the important things we saw yesterday. So basically, yesterday we saw some examples. We focus our attention into examples. We have example one that I will just make a picture to kind of recollect what exactly what was going on. So I started with a field of rational functions on variables x1 and x2, and inside here I have an algebra A that was defined by its generators. So as an C algebra was generated by 5 elements, x1 plus x2, maybe I would put here a 2 and here a 1 just for convenience, plus 1 over x1, x2, and x1 plus 1 over x2. And I will put C here just to recall that this is a C algebra. So just to make it clear, we're only able to take these generators, multiply them, add them, and perform this series of operations. We are not able to divide. Yeah, so the C algebra generated by this is just polynomials in 5 variables evaluated in these expressions. So for example, I cannot invert this element. Okay. And here, well, there was an important drawing of how to get these 3 out of these 3 using a special set of relations. So we say we started with x1, x2, and from here we move to we kind of exchange x1 for another one called x3, and this x3, let's say, was given by the relation x2. Well, I would put like, let me just put it correctly. It was x2 plus 1 over x1, and I got this using my recurrence that I described last talk, and was precisely that, yeah, what I call x3 was this guy, and is x2 plus 1 over x1, right? Like using this this recurrence, xn plus 2 times xn, it's equals xn minus plus 1 plus 1, okay, right? And so on and so forth. I continue, and I keep this one, and then I replace this for another one, that was this one, x1 plus x2 plus 1, x1, x2, and so on and so forth, okay? Maybe I will finish this picture, because I'm going to use it later. I replace this one by x1 plus 1 over x2, x1 plus x2 plus 1 over x1, x2. Then I kind of replace this for x. And here I have maybe x1, and then somehow this was my x4, this was my x5, this would be my x6, and then I have x2, x1, this is my x7, and these are kind of the same, up to a permutation. Yeah? So this was the example, and the other example was, there was like a similar kind of arrangement. Maybe you can see it there. I will just put the other example, was the Grassmannian, and was all the information can be codified in this drawing, right? Here I have the, my algebra was simply, well, maybe you cannot see here. My algebra was the polynomial on 6 variables, 2, 3, up to x34, and I modeled a single relation that was x13, x24, minus x13, 12, x34, minus x14, x34. Okay, and I kind of remember this relation just by using the quadrilateral and the Ptolemy relation. The product of diagonals is equal to the sum of the product of opposite sides of the quadrilateral, right? Diagonals, opposite sides, okay? And here, yeah, somehow I had five things. One that started with the class of 1, 3, and then I had like all the sides, like this guy, this guy, this guy, this guy. So it will be x, the class of x12, x class of x23, so on and so forth. And I have here x, the class of x14, and the sides, x sides. I will put something like this, and the x sides of the quadrilateral. So these are 4 variables, something like this. Okay? So today I'm going to make a framework that will include both of these examples as very, very, very particular examples. Okay? So before I begin, are there any questions about the examples or the lecture of yesterday? Because yesterday at the end we didn't have time for questions, so feel free to ask now anything you would like to ask. So let's start with cluster algebras. So you already see a picture, and somehow these kind of pictures are going to be the combinatorial objects that are going to encode all this information in a procedure. So it will take me a little bit of time, maybe 20 minutes to reach, or maybe more, 40 minutes to reach the definition of cluster algebra, because it has 2 parts. It has a combinatorial part and an algebraic part, and I'm going to be like very clear in both sides. So the first one, it's the combinatorial, and it's not too difficult. So I will have to talk about quivers, okay? So a quiver Q is a directed graph. So they are kind of synonyms, quiver and directed graph, but quiver somehow it's a term that it's used a lot in algebraic frameworks, such as representation theory and geometry. And quiver is a word in English that refers to that thing that where you put the arrows with your bow in the bow. That's a quiver, right? So it's just points and arrows. So a quiver consists of 2 sets. So let's say. So in this sense, a quiver is a collection of vertices and arrows. Yeah. So Q set is vertices, and Q1 is the set of arrows. So it could be something like this. You have a vertex, you have an arrow, you have multiple arrows between these vertices, then you can have another one here, you can have something going back, you could have loops, you can have like an infinite number of arrows between 2 vertices, you could have connected components, they doesn't need to be connected, and it could be infinite. Yeah, this is a quiver, point and arrows. Okay, so we're not going to be as general as this. we're going to take our attention to the following. So we only consider how to put it here, finite quivers. So this means that the number of vertices is finite, and the number of arrows it's also finite. Okay, so I will exclude things that have like infinite number of vertices, infinite number of arrows. Everything's finite here. And the second assumption that I will have that at the beginning doesn't look too natural, but I will elaborate a little bit on that, is that we only consider quivers, without loops. So this is forbidden, nor two cycles. So these subgraphs are forbidden. So we don't want this, we don't want this. Okay? And very importantly, and that's why we'll see, I mean, this example is important. We will assume that the quivers have a distinguished subset of vertices called frozen vertices. And we suppose that there is a possibly empty subset of vertices of frozen vertices, Okay, so things that are frozen, I will denote them in blue. Okay, so an actual example of a thing I will consider is fine. For example, I can have like okay, and maybe some other assumption. It's that in many cases, usual convention, usual notation will be my quivers are finite. Well, I can number the vertices with the numbers 1, 2, 3, so on. So I will assume that that Q0 is just 1 to n, and these are the non-frozen vertices, and the last one, n plus 1 until n plus m, these are the frozen. So these are frozen, this is F, this is F of frozen, and these are non-frozen, and I will call them mutable. Okay, non-frozens, and this is the same as mutable. Okay, so an actual example of what I'm saying it's as follows. So one example, it's I have 1, 2, 3, and I can have 3 cycles. 3 cycles is good, 2 cycles is bad, 1 cycle is bad. Okay, and maybe I have here a 4, and maybe I have frozen vertices 5. 5, 6, and then I have like maybe arrows like this, like this, like this. Everything's, I can have multiple arrows. I can have here 3 arrows, whatever. This could be isolated. Yeah, so this is kind of example of things I will consider, okay? Maybe I should put it here. Like 1, 2, and let's say 3, 4, and 5, maybe like this. Something like this is fine. Of course. 5, let me do this. 6, and 7. Okay, so there might be components without frozen vertices, and yeah. So the, the simplest examples are 1 point and 1 arrow, okay? So somehow this example is going to correspond to this quiver. So that's why it's very particular. So to every quiver, I'm going to construct an algebra. And that's why this is going to be like the simplest non-trivial example, because it will correspond to just 1 arrow, 2 vertices and 1 arrow. And this is going to be special also because it corresponds to only 1 vertex, and it will correspond to having 4 frozen vertices and something like this. So at the end of the day, this cluster algebra, this is going to be the cluster algebra associated to this quiver, and this is going to be the cluster algebra associated to this quiver, okay? That's why there are very special things, because I can consider quivers more complicated like that. I will have more complicated algebras, and just going back to something I mentioned before, this is the reason why these are very, very particular examples, okay? So, okay, so the definition of the cluster algebra, okay? So in order to define cluster algebra, I need to define mutation of quivers. It's a very easy algorithm. So let's example. Example. Okay, so example, I will take a quiver of the form 1, 2, 3, like this. This is going to be my quiver, and there will be non-frozen vertices. Everything, or 1 could be, I mean, I will suppose that 2 is not frozen. 3 might or might not be frozen, whatever, it's the same, it's going to be the same. So I will, this is going to be Q. So I want to compute the mutation in direction 2 of Q, okay? So I have to proceed with these 3 steps, okay? So first step, I will do it here by steps. Step 1, it's I have to look at my vertex where I'm mutating, and I have to add composite arrows, okay? So I have to look at paths of length 2 that passes through 2. Well, there's only this path, right? If I will have 2 arrows here, I will have 2 paths. I will have the path that goes to 1 to 2, and then the first, let's say the arrow on the top, and another that takes 1, 2, and then the arrow below. So here the number of arrows between vertices, it's important, okay? So step 1, I will have this guy, 1, 2, 3, and I add a composite arrow, okay? Step 2, I reverse the arrows that involve 2. And step 3, it's removed 2 cycles. I don't see any 2 cycle, so it just remains the same. Okay? So this is the mutation. The mutation, it's just 2, 1, 3, 2. Okay? Questions so far? Everyone agree that that's the mutation? Yeah? Let's compute again. Let's mutate again in 2. Mu2 of Q. I want to compute it. Okay? So I will have to take this guy and mutate, follow the same steps, okay? This is like the first thing. Let's do it for this. So then I will have to take my quiver as it is, and then add paths, add composite paths. So there I have a path of length 2 that passes through 2. I have this. Okay, this is step 1. Everyone agrees? Step 2 is reverse the orientation of the arrows that involve 2. So step 2, it's 1, 2, 3, and then this. And the step 3, it's remove 2 cycles. And here I see a 2 cycle. Okay, so I have to remove it. Okay. Okay. And that's it. So I get that the mutation in direction 2 again gives me back the original quiver. Okay? So the first exercise is to show that exercise 2.1, second lecture, first exercise, is that, by the way, we're going to check the exercise, some of them tomorrow and the day after tomorrow, okay? Maybe we will take like 20 minutes of the lecture to see the exercise tomorrow and see how, if you were able to, to solve them, and if you need more time, we will come back later. So the first exercise is that the mutation is an involution. Mutation, it's an involution. Quiver mutation is an involution. What do I mean by this? It's that if I mutate the quiver twice at the same vertex, I go back to the same quiver, as the example shows. Okay? This is the first exercise. Okay. So let me just show a little bit a software that, I mean, this looks very easy, but if your quiver is complicated, you don't want to do it by hand. So locally, there's like a very a very intuitive software that is available and it's for free. That was written by my PhD supervisor, Bernard Keller. That's able to do all the computations you don't want to do by hand. And it's very intuitive. So here you can see this is the mutation applet written by Bernard Keller, and it's run in Java. So you just need Java to have it. And here you start with a new quiver, and let's put just one vertex. Okay. So you can just put nodes, and then add arrows. I put an arrow from 1. So I click, and I took one arrow from 1 to 2. I click in 2 and 3, and this gives me this other arrow. And then let's say that's my quiver. I can start mutating by clicking, and here you see how we get the example we started with. Okay, and you can continue, and this gives you like all the things you want. Okay, so you can iterate mutation. We're going to do that. Iterate a lot mutation. Okay. So we're going to perform this operation, and we're going to do it over again in all possible directions. Okay? So just to get the feeling that, to see that this is really a non-trivial operation, let me show you an example. So let me just add, consider a quiver that has the following shape. Let's imagine that I have 2 arrows. So here you can see a 2. This is a 2. And let's put 3 arrows here, okay? Okay, and let's start mutating. So first, I will mutate in 1, 2, 3, or in 1, 3, 2, 1, 3, 2, 1, 3, 2, and I will just perform that sequence of mutation, just a sequence that I like. So I mutate in 1, and as you can see, the direction of the arrows involving 1 change, right? You can see these 2 go in the other direction. I will go back. These 3 that go from 1 to 3, then they change the direction. And then these 5 arise as composite mutations. Why? As composite arrows. Let me go back. If I have 2 arrows from 2 to 1 and 3 arrows from 3 to 1, I have 6 possible paths of length 2 that passes from 2 to 3. You see? These 2 and these 3 give 6 possible combinations, right? First, 1 of these 2 arrows, and then 3 of these 2 arrows, and then I get 5. So then we have 6 arrows from 2 to 3, and I have to raise 1 because we have the other direction. I have this 5. Okay? That's why I have this 5. Everyone's following? Okay. Now I would do 3. I have 13, 3, 5, 2, 62, 801, 49,000. I don't know how to read this number. I don't know how to read the number neither. So, you see, I'm starting to get crazy big numbers. They don't fit the screen. Okay? So even if this looks like a very easy and simple operation, this can lead to things that are out of our hands. I mean, I just perform maybe like 10 mutations or 12, I don't know, and then I got things that I cannot longer deal with. And this will just explode. And I'm just considering this particular sequence. Okay? So quiver mutation can be, iterated quiver mutation can be very wild. Right? Yeah? So that's kind of the upshot. Observation, iterated quiver mutation is wild in general. Okay, so nowadays we know which quivers are actually easy quivers, those that will not produce this phenomenon, those that will only have a finite set of quivers that are mutation equivalent to it. Okay, I'm already introducing some terminology. That's a classification theorem that we know, and that's why here I have only finite number of things. This is going to be a quiver that only has like finite number of different mutations. If I mutate this at 1, I just oppose it because we have, this example is too small. Step 1, it's empty. And so if I mutate this in iterated times, I only flipping the orientation. Yeah, and this I can only mutate here. I reverse the orientation of everyone and that arrows. And if I can only mutate twice here, know that there's an involution, and that's why I see that there are only 2 things. Right? Because I can only mutate in 1, and this exercise tells me that I have an involution. So if I mutate in 1, I go back to the other guy. Okay? I'm going a little bit of steps ahead, but I want you to be building the intuition of what's going on. Okay? Questions? Why? It's because, I mean, I'm just following an algorithm, and basically they are coming bigger and bigger because imagine mutating 1. Okay? So to mutating 1, I have to consider path of 2 that goes through 1. So I will have to consider paths that from 2, 1, 3. Okay? And I have this number of paths going here and that number of arrows going there. So in order to find the number of paths going from 2 to 3, I have to multiply this number times this number. So if I have a big number times another big number, that's very big. And then I just have to subtract this number that it's big, but it's not as big as the product of them. That's why it just gets bigger and bigger and bigger. Yeah? I mean, I think like if you go down back a little bit, you can see like the effect I'm saying. So from the beginning, it's, yeah, I have 2 paths and 3 paths that I can compose. This gives me 6 in that direction. I only have 1 in that direction, okay? So this gives me a 5. Now, if I do 3, if I mutate in 3, it's going to be these 5 paths times these 3 paths. That's 15. And here I only have 2. So I will expect 13. And it's exactly the number I have. Here I do 5 times 13 is 50, no, it's 65. Minus 3 is 62. So here I will have a 62. Yeah? So it's just like a multiplication of big numbers minus not a such big number. If you do this enough times, this phenomenon explodes. Okay? Okay. So that's the combinatorics. That's the combinatorics. And let me just, yeah, now go to the algebra. Okay. Let me see time. Okay. Now I will go to, just like, let me just add here a remark, n regular trace. Okay. I'm always supposing that n is the number of mutable directions, and n plus m it's the number of frozen directions. Okay. So the let me just put again here. Q0 is 1 to n plus 1, n plus m, and these are the frozens. So the case in which frozens it's empty corresponds to the case m equals 0. Okay? So the definition is let Tn be the n regular tree. That is, in other words, Tn is the unique optoisomorphism of graph. Isomorphism, a connected graph that is n regular. N regular means that every vertex has n neighbors. Every vertex has n different neighbors. N different vertices connected adjacent to it. And so this is the unique connected graph that is n regular and has no cycles. So, for example, T1 has to be, so this connected graphs that have no cycles are called trees, and if they are n regular, they are n regular trees. Okay, so T1 would be, well, I have to have a vertex, and this vertex has to have one neighbor. So this is one, and this vertex also has to have one neighbor. So this is just T1. Okay, somehow like this guy. T2, it's just, well, I have a vertex, it has to have two neighbors, and each one has to have two neighbors. So it's an infinite graph that looks a little bit like this. Okay? And it's somehow the covering of this graph. This kind of, this is a quotient of T2, for example. This pentagon, this is like a pentagon. T3, it's, well, I have a vertex, and I have to have three neighbors, and every neighbor has to have three neighbors, and every vertex. So it's infinite tree. And you see why it's unique, because I'm just constructing it by the definition and the properties, okay? And this is infinite, infinite, infinite. So this is T3, okay? So the observation, I will maybe erase example. Observation. So a little bit to put order in this mutation, I can consider these trees. So definition, we say that Q prime mutation equivalent to Q if Q prime is equal to, well, you mutate many times Q to reach it, okay? I1 to IR of double vertices. Okay? So the observation is the Quivers mutation equivalent to Q can be organized on the vertices of Tn. So here n is the number of mutable vertices. Okay? So how do I do that? I just make a choice. I pick a vertex of the vertex tree. Let's say n equals 2, example. N equals 3. And then I pick a vertex of I just choose it, and I assign here Q. And then what I'm going to do, it's label the 3 incident vertices to this vertex by 1, 2, 3. I just make a choice and label them. So here in this vertex, I will put mu1 of Q. I will put here mu2 of Q. And I will put here mu3 of Q. And then I can mutate again. So this is already 1. And since the mutation, in the example, the first exercise was that the mutation is an involution. If I perform again mutation in direction 1 of this guy, I go back to this. Yeah. So then this is already, I mean, I don't have to mutate this in 1 because I already get back to 2. And I could put here, say I put 2 here and a 3 here. Here we have mu1, mu3 of Q. Here I will have mu2, mu1 of Q, and so on and so forth. Indexing by the ruler tree, it's going to be very helpful to describe this, to put your hands on this mutation operation and iterated mutation. We usually consider these trees just to index the, just to have a little bit more of a control on the possible iterated mutations of a quiver. Okay? Questions? No? Okay, now I'm going to the algebra. Why? Okay, as I was explaining in the history of cluster algebras, in the 90s, there were like 2 important avenues of research, like total positivity and quantum groups. And in that same total positivity, there are many examples such as Grassmannians and other varieties like Flack varieties. And the relations, there was lots of combinatorics behind it. For example, here, they would see like the relevant combinatorics will be for the Grassmannians for things of the Grassmannian to Cn. Like many of the relations between the generators of the corresponding algebra can be encoded in a polygon. There were other varieties that were important, like the Flack varieties. And they will see that there are like something like braids that also give like the relations of the ring of coordinates of the Flack variety. So there was always in these examples a combinatorial component. Polygons, braids, Plaby graphs, many things. And in those 10 years, Fomin and Selevinsky wrote lots of papers and tried to see combinatorial aspects of that theory. And they somehow reached, like, they figured out that there was like a common language, that was the language of quivers and quiver mutation, that encoded all the examples at the same time. So let's say that this definition arose from 10 years of research of Fomin and Selevinsky, where they kind of said that in every variety they wanted to study, there was like a big combinatorial framework, and all those frameworks could be encoded by a single combinatorial framework, that is the quivers. So this is like a definition they arrived after 10 years of research. This and what's going to follow, okay? So yeah, at the first hand, it doesn't look like so natural, like why? But let's say it's one of the discoveries of Fomin and Selevinsky, that this is an actual important operation. Also, for example, the braids moves that Bruno was describing yesterday, they can be put in the language, they can be expressed in the language of quiver and quiver mutation. So it's somehow a combinatorial framework that it's being universal in many settings. Okay, so I will erase this. And I will talk about quivers and seeds. the way, this could have been my first lecture because I'm just building the theory of cluster algebras. But without examples, you will, questions like yours will arise, like, why are you doing this? So first, I'm going to show that what I'm doing can produce these examples as very particular examples. And then I'm going to give more about the families of examples that fit this framework, okay? Let me see if I'm not forgetting anything. Okay. Okay. So clusters and seeds. Let me just see how I want to express this. Okay. So never forget this convention. Let F be the set of rational functions with closed complex numbers. Actually, here it's enough to take Q. But since I want to talk about examples coming from algebraic geometry. In algebraic geometry, you usually consider a field, and we want this field to be algebraically closed. And some of the things are valid in characteristic different from 0. The only characteristic that is not good for the theory is characteristic 2. There are some pathologies. But let's say that all the theory can be written in terms of rational numbers. But let me just put C because, yeah, it's not going to be a big change. So I consider F to be the field on rational functions on many variables, and how many variables? As many as vertices I see in my quiver. So here I will have like the field of rational functions on 5 variables. Here I have rational functions on 2 variables, right? And okay, and definition. A cluster in F is a collection, is a subset U1, UN plus M of elements of F such that 1, the set, and I will call it U bar. U is algebraically independent over C, yeah. Everyone is familiar with field theory, like basic things like field extensions and algebraic independence. Yes. Okay. So this means that these expressions do not satisfy polynomial relations. Okay. For example, x1 square, not a cluster of let's say x1, x2, because these guys satisfy a polynomial equation. The square of this is equal to this, right? But this is a cluster. Yeah? And actually, all of these are going to be clusters in this field. So this is a cluster here, this is a cluster here, and this is going to be a cluster here. These two guys do not satisfy polynomial equations. These two guys do not satisfy polynomial equations. So here you have 5 examples of clusters inside this field, okay? And the second property, and I haven't mentioned the property, the second property is that we have that the field itself, it's the extension of C by U1, UN plus M. This means that the smallest field, in other words, the smallest subfield of F containing C and U is F itself. Okay? So for example, if you consider these two elements and consider the scalar C, and you ask for what's the smallest field inside F that contains C and that contains these two elements, it's going to be all the field F. In other words, if I start, since I'm considering fields, if I start to multiply, add, invert, multiply, add, invert, multiply by scalars, and perform these operations, I can build any element of this out of these two. Okay? That's the, for example, why x1 is here, why x1 is in the smallest field that contains these two guys and these two guys. Well, now I'm able to invert this one. So I invert this one, it's in that field. Then I add x2 plus 1. So I add x2 plus 1, it's in the field, in the subfield containing these two elements. And then I multiply it by the inverse of this guy, and then I get x1. So in particular, x1 is in that field, and since I already have x2, then I get the whole field itself. Okay? So these are the only two conditions I need for a cluster to have a cluster. And this is, well, there's a definition that I didn't know if you know. This is that U is a free generating set of the field. Okay? That's another way to say these two terms. It has a definition. And so in other words, U is a free generating set. And any free generating set of a, I mean, this is not important, but I'm using a little bit of field theory terminology just to explain a little bit what's going on. This is a field extension of degree n plus m, and any free generating set must have n plus m elements. That's why clusters have size n plus m. So this is not like a choice. This is a necessary condition. Okay. Anyways, this is not going. This is as much as field theory as we will use in the lecture. The rest is just going to be high school algebra. Okay. So the definition: a seed in F is a pair. Is a pair. Let me call, well, since I'm fixing Q, I will just put, this is not the same Q. It's a pair of, you know, like, let's just change words and put, what's a good word for quiver? Q, delta U, where delta is a quiver, you know, without loops and not two cycles, and the number of vertices is n plus m, and the number of yes, and U is a cluster. Yeah. Okay. So it's just like now I'm not only considering quivers. I'm going to consider this cluster. So for example, this could be a cluster. 1 goes to 2, it's my quiver, and my free generating set, and my cluster is this. This is a seed. Okay? This is a seed inside here. Okay? And now what I'm going to do is to define mutation of seeds. And mutations of seeds will include mutation of quivers and mutation of, well, how to change this cluster, and it's essentially a way to express this step here and this following step here, and so on and so forth. Okay? So, okay. So I will erase here. Mutation of seeds. Okay. So let delta U be a seed in F. And Q an element and Q a mutable vertex of delta. Okay? So I choose a seed and a vertex. The mutation of this seed in direction K is, it just mutate your quiver and construct a new cluster where, so of course I already spent some time explaining how I mutate the quiver. Now I'm going to say you how I construct the new cluster. So the cluster U prime, it's just going to be your cluster U, and you exchange, like here, you just exchange one single element of the cluster and replace it by a new one. So I'm going to remove from UK its K term, and instead of it, replace it by a new guy called UK prime, okay? And UK prime is going to be given by a cluster transformation or an exchange relation. And here UK prime, it's going to be, and I'm going to write an expression here that looks like what I was saying you, a monomial plus a monomial over a monomial, okay? So here the monomial, it's, the denominators is UK, like here. You see here, I'm replacing this guy by a new one, and this guy appearing in the denominator. Same here. Well, we cannot see it because we perform already some sort of simplification of the expression, and somehow this term cancelled, and the explanation that I explained this last time. So here I will have two monomials, and I'm going to write and then explain. This is going to be the product of all the variables UA, and I will have a variable UA anytime I see an arrow from I to K, okay? And then I'm going to put the variable UJ every time I see an arrow from K to J, okay? So I'm mutating in K, so I have to look at the arrows that point to K, and this codifies a monomial, and then I have to look at all the arrows that receive an arrow from K, and then construct out from that monomial, okay? So this is my exchange relation, okay? So this is going to be called either exchange relation and geometers like to call it cluster transformation also, cluster or cluster transformation. So it's a cluster transformation. Like in geometry, it's better to call them cluster transformations. There are these kind of transformations have nice geometric properties that are expressed in terms of volume forms and other things that I don't want to talk about right now, but I just want to make the point that these look like very specific, but they enjoy like very nice geometric properties, okay? Okay, so maybe I will give an example. First of all, there's something to check, right? Why? I gave a definition of what's a cluster, right? So this new guy has to be a cluster. So the second is that U prime is a cluster of F, okay? So this U prime should satisfy these two conditions, okay? Perfect. So let me just give an example now. And I will put some like helpful notation. Yeah, so this is a lot of notation, right? Why? Because I'm repeating 1, 1, 2, 2. So what I would do, it's like we put xi on top of vertex I, okay? So let me have one example of this. So for example, if I consider my seed to be 1, 2, 1, 2, 3, and then my cluster to be x1, x2, x3. So this is writing a lot. So I will use my notation and write all this information like this. Okay? Then let's assume that all are mutable. Let's assume that the set of frozens it's empty. So I can mutate in 1, in 2, and 3. Okay? So then this seed admits 3 mutations, x2, x3. I can mutate it in direction 1. I can mutate it in direction 3, 2. And I can mutate it in direction 3. Okay? Let's mutate it in direction 1. So I have to mutate. Let's mutate it first in direction 2 because I know how this quiver changes. I know that the quiver changes a little bit. That was my first example. It mutated like this. Okay? I'm mutating here. Right? Exchange relation says that you keep all, but you replace the variable where you're mutating. Right? So we keep this and this, x1 and x3. And let me just put, actually, I'm going to modify a little bit the example to make it more interesting. I'm going to put 2 arrows here. So I will have 2 composite arrows here. Right? It's very similar to the past example. Just I just put like 2 arrows here. So I have 2 arrows. So then instead of composing 1 arrow, I have 2 paths. The first one with the top one and the first one with the second one. Okay? So then I have to put something here. Okay? What do I put? Well, I just follow this prescription. So I'm exchanging x2. So x2, it's going to be in the denominator. This is an x2. Okay? Now, I have to have a monomial here and a monomial here. The first monomial tells me which vertices point to 2. Yeah? How many vertices have an arrow that goes to the place I mutate to. So I only have x1, so this is going to be x1. Okay? Now, the second tells me, codifies the arrows that point from 2 to 3. I have 2. I have this one and this one. So I will have x3 square. Okay? Now, this is the mutation in direction 1. Let's do the mutation in direction in direction 1. It's well, I have to mutate the quiver here. So there are no paths of length 2 going through 1. So the first step is empty. I just have to reverse the arrows. Yeah. So the quiver is going to be like this. Are we fine? The quiver, this is the mutation of the quiver in direction 1 of that quiver. Okay? Now I have to replace this guy for a new one. So, well, the other 2 remain the same. Right? Let me just put here. Okay? So here I have to replace something, and I know that that something, it's going to have x1 in the denominator. Right? Because it's the one I'm replacing. So I have to look at the arrows going to 1. How many arrows there are? There are 0. So this product is an empty product. What is an empty product? 1. Very good. 1. And then I have to codify the arrows that go from x1 to x2. Right? So this is x2. Okay? And what about this guy? So again, I will do it faster. I only have, I'm going to keep these two. I'm going to mutate here. So I just have to invert the arrows because they are not paths of length 2. I have to divide in between x3, and this, the first term is x2 squared, and the second term is an empty product, is 1. Okay? So for example, in this example, if I let this to be my seed, x1 goes to x2, right? If I'm mutating 1, I have to replace x2, the quiver mutates, and I have to see, well, I know that that the quiver is always going just to change the orientation, and if I perform, this guy is going to be exactly the computation I did before. It's going to be, so I have to replace this, so it's x2, and then I have to do this plus 1, right? Again, the arrows that go from here to here, that enter is just 1, and the arrows that go from here to here, it's just, and it's precisely x1, x2, 1 plus x1 plus x2, something like this, okay? So it's exactly the same, right? So yesterday we were actually, I mean, the computations done yesterday are, I hope I'm convincing you that these are just an instance, an example of a mutation of seeds, right? Same here. Same here. Same here. My cluster would be, it's not visible to everyone, but I mean, if I have time, I will explain it. If not, you have to convince yourself that here I'm doing exactly the same thing. Okay? I want to reach to the definition of a cluster algebra. Let me just mutate again this in 2, right? So if I mutate again in 2, I know that the quiver is going to the quiver is an involution, so I know that I'm going to get to the same quiver as before. I keep this 2. I'm sorry, I keep this 2, right? And how do I have to replace this one, right? I have to replace this one. How do I do? I'm going to perform the computation here in red. I have to replace this one, so this one goes to the bottom, right? And I have to have 2 monomials, right? One monomial encodes the arrows that go inside of it. So it's going to be, I'm sorry, you didn't tell me. Here I have 2 arrows, right? Here I have 2 arrows because yeah. So I have x3 square, right? And here I have x1 square. And these 2 cancel with each other, and this gives me just x2. Okay? So I go back. If I do mutation twice at the same vertex, I go back to the same original seed. Right? So the exercise number 3, the exercise 2.3, it's that seed mutation is an involution. If I do mu k of a seed, I obtain the same seed. This is an example of it, right? And it's it's not as complicated. I mean, if you already done the first example, you know that the quiver is going to be the same because I'm just mutating twice at the same vertex. And here you see what's going on. Like somehow what I'm dividing, it's the same, you know, like the 2 monomers will appear. The same, just, the 2 monomers will appear because I'm just exchanging the orientations of the arrow. So let's say, using a little bit like Bruno's terminology, this can be the positive monomial, and this the positive monomial, and this the negative monomial. Here, now they changed roles. This would be the negative monomial, and this is going to be the positive monomial, just because I changed the orientation of the arrows. But it's the same binomial. So then it cancels, and then this guy goes up, and that's a sketch of the proof. Okay? Very good. So this exercise, it's easy if you already done the first exercise of the class. And yeah, so another observation is that iterated mutation can be a so iterate observation Okay, definition, we say that two seats delta u and delta prime u prime are mutation equivalent if delta prime u prime it's equal to mi1 mir of delta u, just as before. Okay, and we write these are mutation equivalent. Delta u, it's mutation equivalent to delta prime u prime, and u, it's mutation equivalent to u prime using the quiver delta, right? Why? I mean, this is important. I cannot say that two clusters are mutation equivalent if I don't fix a quiver, right? Because, for example, if I consider this seed, it's not going to be the same as if I consider this seed, x1, and then I put two arrows, right? They have the same cluster, but when I start mutating, then I will get x. Then I will get x. If I replace here, they say mutation in 1, I divide in between x1, and I get 1 plus x2 squared, right? So it's not the same. It's not the same. Really, I cannot say that this cluster is equivalent to this cluster. That's not well defined. I mean, it depends on a quiver. That's why when I talk about clusters, I will say like which is the quiver that is producing me that relation in between them. Okay? So okay, now we are ready to define a cluster algebra. Okay. Okay, definition. Let Q be a quiver. So first of all, we will let x to be x1 through xn plus m. So as always, I will suppose that Q it's 1 to m plus m, and that the frozens are the last n m vertices. Okay? So this is the initial cluster. Is the initial cluster. Just like in this example, I have some initial conditions. It's a little bit like a dynamical system. I have some initial state, and the way I start like changing, it's like in a dynamical system. It's given by an expression. I have a way to describe this dynamical system in terms of a function, but in a dynamical system, you just have time 0, time 1, time 2, time 3. It's discrete. This dynamical system, time is ramified. I can go as the times are parameterized by the vertices of the n regular tree. Yeah, so it's and the iteration rule changes every time. So it's like a very complex dynamical system. Okay, it's initial cluster, and yeah, this is going to be the initial seed. Is the initial seed. And second, it's I will let xq. It's the set of all. So here, the name of the game is you start with certain initial expressions, you have your quiver, and you start obtaining new expressions. So I will put a name to the set of all the expressions that I can obtain. So xq is the set of all the expressions that I can obtain mutating q. How do I write that? It's just take all the clusters and unite them for all the clusters that are equivalent to the initial cluster using q. Okay? Yeah, this is the set of cluster. This is this notation, okay? So I'm just starting. In other words, I with the seed, I play this game, and I collect all the rational functions that I produce. Yeah, is the set of cluster variables associated to Q. Okay. Why variables? Because these are free generating sets. When I say that these are algebraically independent and that generate this, is that these are like variables. This could be Y and Z. They have no relation between them. That's why they are called variables, because they are algebraically independent and generate the field. Yeah, so that's a little bit explanation of why we say variables. Yeah, they don't have relations in each other. And finally, the cluster algebra associated to Q is AQ, and it's just the algebra generated by the cluster variables, okay? As a C algebra. Is the C subalgebra of my ambient field F generated by the cluster variables, okay? So in this case, this is my first example of a cluster algebra, okay? I start with an initial cluster, I start mutating. I hope I already convinced this example with the recurrence I raised here can be put in terms of this quiver and this mutation of seeds. So this would be the first cluster algebra, okay? The natural question that arises is why this is interesting, why this makes sense, okay? And it's the easiest thing to communicate why this is interesting. And what I'm going to do is like provide many examples that show that this is actually interesting because it can describe many different frameworks using a unifying language, okay? And yeah, for example, I can tell you there's a projective, well, there's a variety that whose coordinate ring is described using these expressions. But also in this theory, actually many of these polynomials codify invariants of varieties, codify invariants of quiver representations of algebraic objects. So this that's another possible answer. Like these expressions that I am obtaining are codifying invariants of varieties, right? So it needs a little bit more of time to elaborate how, for example, this expression codifies invariance of a variety. Actually, the coefficients appearing here, 1, 1, 1, codify topological information of a certain variety, associated variety. This monomial codifies algebraic information of a certain category. So I mean, already in the first lecture, I told you like a little bit of the history of this subject. In the history of this subject, I told you, okay, this framework was built to address total positivity in reductive groups and canonical basis in quantum groups. But in the first 10 years, people start realizing of all the properties I'm saying, like, these are actually like codifying topological information of these varieties, and these are algebraic information of these categories. And that's why this field became very interesting to many people. So there's people in all around the world doing this theory and like finding the connections with other areas of mathematics, okay? So at first glance, it's not obvious, but if you're interested, just come to me and I can explain a little bit further. Okay, so let me just, yeah, so I have like 10 minutes. So in the last 10 minutes, I'm going to put like a set of theorems that actually make sense, and I think you will be able to understand the statements, and that already give you like, I will do a little bit of software demonstration to see how non-trivial this is. Any questions at the moment? No? Okay, I continue. So okay, let me just put like the example of the Grassmannian here, how it's an example. So the example of the Grassmannian is you just pick that example, the example of the Grassmannian 1, 3. This is going to be your cluster. X maybe I will put here X 1, 4, 1, 2, X 3, 4, and maybe I will put it as an exercise. X 1, 2. I have to do a quadrilateral. 1, 2, 3, 4. So it's 1, 2, 3, 4, 1, 4, 2, 4, 2, 3. So the exercise to show that this is the seed giving rise to the cluster structure on the Grassmannian. So exercise 2.3, 2.4, 2.3, 4? Okay. Which one is it? 2.3? Ah, yeah. 2.4 is show that this seed, this one, gives the cluster structure on the coordinate ring of the Grassmannian of two planes in C4. Okay? So as I'm telling you, this is not a property, it's a structure. So what's the structure? It's find a quiver and a set of functions in this ring, or elements of this ring, that actually, that such that if I mutate this seed, I can generate this ring. Okay? This is very easy. As I told you, I only have one mutable vertex, so everything will be encoded in the 1 or 3, so I just have to mutate once. I just have to verify that the relation I wrote, it's an exchange relation. Yeah? So like that quiver, if I apply the mutation relation to that quiver, then I obtain the Ptolemy relation or the Plucker relation of the Grassmannian. Okay, it's kind of an easy exercise. It's just a check. It's not an exercise. Just check it. I already gave it. Okay. So finally, properties of okay. This is an easy theorem. Maybe I will not show it this class. I will show it. I will make a proof next class because it's easy. It's that AQ is independent of the initial cluster. Yeah. So for example, this is another cluster that I could have considered that produces me the same cluster algebra. So I mean, I don't need to choose x1 and x2. I can put like any other cluster, and I will obtain isomorphic ring. Okay, it's independent of the initial cluster, so I could change this for whatever I want. Yeah, and the second is that, and moreover, it only depends on the mutation class of Q. For example, so I will prove this next class. If I have the cluster algebra associated to 1, 2, 3, this is isomorphic to the cluster algebra associated to 1, 2, 3, because these two quivers are mutation equivalent. Okay? Second theorem. Second theorem. It's called the Laurent phenomenon. the Laurent phenomenon, it's that phenomenon is pH or F? Phenomenon, I forgot. I think it's in French it's with pH. Okay, the Laurent phenomenon is that this is a theorem, and it's by Fomin and Selevinsky. (2001), and it's the following: for every Q, the set of cluster variables it's contained in set x1. It's a Laurent polynomial in I have to invert the mutable variables, and the frozen variables I don't need to invert them. Okay? So somehow this is the Laurent phenomenon. Yeah? In the Laurent phenomenon, how did I obtain this expression? I obtained this expression by maybe this expression. Maybe this expression I obtained it like yeah, there was a cancellation, and the cancellation produces me. I think I was careful in this example, and maybe just put it here. Here you can see the Laurent phenomenon. How did I get this cluster variable? This is x2 plus 1 over x2. This is just x1. This was something like x1 x2 plus x2 plus x1 plus 1 times x2 over x1 plus 1 over x2 x1 x2. Okay, somehow if I just follow the relation, I obtain this expression, and there was a magic, that is that I obtain a Laurent polynomial. Okay, so this is very important. This is very impressive, because in general I will not expect Laurent polynomials. In general, I would expect rational functions. So this theorem is telling you that this magic is not a special of this example. Any other example will have the same properties, and it's also like has some integrality. When I divide like a polynomial with integer coefficients by a polynomial with integer coefficients, what I expect is a rational function with rational coefficients. So it's not only telling you that I'm not getting rational expressions, I'm getting integral expressions. So there's a little bit of enumerative geometry going on. And the conjecture, and I will finish here. Maybe I will just do a bit of software demonstration, or maybe next class. Conjecture is the positivity conjecture. Conjecture, it's that xq, I don't only get integers, I get positive integers. All of these are positive. And this is actually non-trivial. Imagine you take a polynomial with positive coefficients, for example, x1 to the cube plus 1, and I divide it by something that has positive coefficients, x1 plus 1. What I get is something that does not have positive coefficients. Okay? So dividing things with positive coefficients can lead to negative coefficients. So imagine here, I'm just like, imagine the first example in which I have like lots of, maybe to appreciate this example, think of my software demonstration. In my software demonstration, I get like these crazy big numbers. So using the exchange relation, I will have to iterate this, and I will produce like crazy, very big terms that I will take the power of very big powers, and I will add, and there will be a cancellation, and the cancellation always lead to integers, Laurent polynomials with integer coefficients, and actually they are positive. Okay? And there's actually, this conjecture was open like for nearly 20 years, and now it's a theorem. Theorem. And I will finish this here. Theorem by, I will just write the names and mention a little bit. Theorem by Gross, Hacking, Kill, and Koncevich. Gross, Hacking, Kill, and Maxim Koncevich, a Fields medalist. Koncevich is that this was done in 2018. The positive conjecture is true. Is true. Okay. So maybe you know this guy. He's a Fields medalist, and these three are algebraic geometries working in birational geometry. This is a very long paper. It's like 130 pages, published in the most prestigious journal, Journal of the American Mathematical Society. It's like a very long paper with very strong authors, and the proof of this theorem, I mean, the statements, I think you understand them. They are basic. They only involve like high school algebra. The proof uses lots of geometry and mathematical physics. They use something called mirror symmetry, that is a theory that arose in string theory in mathematical physics. So it really shows how difficult was this theorem, like, or this conjecture. You really need to use highly technical geometrical techniques to prove it. Okay, so here proof uses mirror symmetry, a branch of string theory. So that's why it's this topic is very interesting. It really appears in mathematical physics, in birational geometry, in knot theory, in hyperbolic geometry. So it appears in many places, and somehow the framework is very easy. It's combinatorial. It's just like high school algebra. All the main theorems you can see in the easiest example. In the easiest example, you can see the positivity conjecture. You can see the magic of the Laurent phenomenon, and that's why this theory it was very successful, because in the simplest example you can see how non-trivial are all the important statements. Okay? So I will end up here. Okay, the field comes into play because it's just like an ambient field, just like things going on in the field, but the field itself, it's not like so important from the algebraic perspective. From the geometric perspective, the field, it's important because the field comes important in geometry. So for example, yeah, let's explain this in a bit detail. So cluster algebras are going to be important in geometry. So in geometry, you will have a variety, right? A variety. And a cluster structure in a variety is just going to be an atlas. So you have like open pieces, and these open pieces are like the seats. So this might be just like a local chart, and that has coordinates x1, x2. And this maybe I have another chart with other coordinates. And the cluster transformation is just the change of coordinates. It's just going to be, let's say, z it's equal to x1, and y it's equal to x2, x1 plus 1. So the clusters are just charts in a variety. Cluster transformations are just the change of coordinates. The field itself, it's going to be the field of functions on every chart, and actually the change of coordinates is birational. So when you iterate this, you obtain a birational set of coordinates, and well, to express this birational set of coordinates, you usually use the fields. The fields are just like the field of functions on each chart, and the birational and the cluster transformation is just the birational function giving you the change of coordinates after many changes of charts, right? So that's, I mean, like the field comes more the importance of the field it's more clear when one starts talking about a geometric, well, algebraic varieties and the change of coordinates between, well, of an atlas. Yeah, so the cluster structure is the cluster structure on a variety is just like you can think in your head that it's just like a specific atlas that gives you nice coordinates. So you know that coordinates in varieties are important. For example, spherical coordinates can express very simple dynamics on a sphere, for example. And cluster coordinates are also like coordinates in a variety that are very convenient to express like certain processes related to Poisson geometry or to algebraic geometry. So if you want another way, like a geometric way of thinking of what I'm explaining, it's distinguishes atlas in varieties that provide set of coordinates for which that express very simple, interesting physical dynamics.